So with that, I'm going to get into how we do it. And I'm going to focus, so for you guys who are techies, I saw a bunch of developers. Show me hands again, developers. You guys are pretty technical, right? How many know Java? Did I ask this already? Java? Okay. So I'm going to talk to you about Hadoop, and so you guys can kind of get a feel for what this is. So we have not had difficulty building big, complex systems, right? In fact, going back 20, 30 years, we've built these large clusters of servers to deal with tremendous amounts of data. The only problem is they were very expensive. We could build these server rooms that would fill this room full of servers and more, entire buildings full of servers, and we could process tons of data, but it was really expensive. It wasn't really for you and me. It wasn't really for a startup, right? Company. And so when you code for one machine, that's fairly simple, but when you code for many users, when you code for many systems that are working together, there is inherent complexity, right? The administration of the platform, you have to think about how you're going to program for the platform. How do I program, in a way, a question that gets solved, that can spread that problem around across many servers? Not really an easy thing to do. Cost prohibitive, scalability, managing that, transparency, resiliency, all those things. So again, not that we haven't done this before Hadoop, but Hadoop has made this significantly easier. So Hadoop is this open source software, which just means that it's kind of free to the world, right? If you want to go and download it, you can download it, you can use it, no strings attached, right? If you want to make changes to it, you have the option to contribute back and maybe improve it, and everyone can benefit. And it was inspired by some work from Google, where they published a paper on MapReduce, Google file system, this is called Big Table. Yahoo had a problem that apparently was solved by this paper that introduced MapReduce, so they were very excited by that. So they created this, and the thing that we're actually using was this called Nutch, which was to kind of crawl the web and grab all this information. And so they had scalability problems with the original Nutch project, and so they looked to this MapReduce to help them solve that. And so, the powers that be came out, they did this thing called Hadoop, they contributed to open source, and a lot of people started getting excited about it, and so that's how it came to be. So it's cost effective, and I'll get into why, but it's a platform that allows us to do massive parallel computing on common servers. And when we say the word commodity, we don't mean cheap. We don't mean go to your basement, find the computer that you had back in high school, and use it for a Hadoop cluster. What we mean is, when Dell makes a motherboard for a server, the server that they're going to sell millions of units of, they're just printing those boards, right? Really, really, a couple per minute probably, or per second. And so that production scale brings down that cost. We're not using specialized memory. We're not using specialized parts. You're not using specialized power supplies or anything. It's just stuff that they're producing en masse. So when you produce something at that quantity, it just drives down cost, right? Before this, we would use these very expensive servers that were highly engineered to do weather forecasting and things like that, right? These high performance computing environments. So Hadoop allowed us to get this capability with commodity servers. It's scalable in that I'm going to show you what happens, but you can actually combine a bunch of nodes and add more nodes if you find that you're running out of space or you need more performance. It's fault tolerant. Let me talk about this. If you're familiar with how we build database systems today and before, you might use a SAN, you might use a RAID array, right? So for those who don't know, RAID array is, it would really suck if my database went down if my disk drive failed. So what we do is we take a bunch of these disks, we combine them, and we build what's called a RAID array. And if one drive fails, we get an alert. But the data was striped across those drives with some ability to kind of sustain losses. And you have an opportunity to go in there and change a disk, put a brand new one, and then it just kind of recalibrates itself, restripes the data, and you're kind of back in business, right? But with Hadoop, if I have thousands of disk drives and hundreds or thousands of nodes, I could have one person dedicated to changing drives all day long. And actually, RAID controllers are not cheap either, right? They cost money. Can we do without? So Hadoop is a platform that allows us to actually do away with RAID arrays completely and just deal with, if a node fails, I'll go for lunch first. come back and deal with it. And I'll show you how it happens. It's also flexible in that if someone asks, what is Hadoop? My basic answer, if I had only one moment, I would say it's basically a big file system. Think of it as a big file system. And we can do stuff on it. Because that's about as precise as we can get. It's a file system that we can do stuff on it. And what we can do on it is extremely vast. So there's no point in me getting started. But because it's just a file system, I can put anything on there as long as it's a file. Maybe it's a JSON format. Maybe it's a structured binary format. Maybe it's, I don't care. As long as I can write it as a file, I can put it into Hadoop. And I can run analytics on it. So here's a picture of the cost advantage. I stole this chart from someone else, VMware Hadoop Summit 2012. So the numbers aren't important. It's really the orders of magnitude change that's important. So if I had $1 million, right, I'm a company probably, organization, I got $1 million to spend, what would I get for that? If I was choosing SAN storage, which is storage area network, I would get, half a petabyte of usable storage, 1 million IOs per second, and maybe 1 gigabyte per second transfer rate. Again, the numbers aren't important. They'll probably change by now. Likely are. And you go, well, that's really high performance storage, and I can run my enterprise database servers on it. But then you go, well, can I get something less expensive per gigabyte and get more of it? So we might go to what's called NAS filers, or network attached storage. And so $1 million gets me 1 petabyte of storage, and less IOs per second, so lower performing, and more transfer rate per second. Okay? And then finally, what Hadoop does is Hadoop does away with NAS files and SAN storage altogether. Now, there are some deployments of Hadoop that use SAN storage, okay? So I don't want to overgeneralize, but the pedigree of Hadoop is that I'm using these commodity servers that are printed in the thousands or millions per whatever unit of time you want. Okay, so the cost is lower. And rather than having RAID controllers, I'm just going to plug a hard drive directly on that box. If I'm not going to plug one drive, I'm going to plug 6 or 12. HP now has a server, I think, was like 40 drives or more in a single chassis. So you got 40 drives at 10 terabytes. That's 40 terabytes of raw usable storage on a single node. Not for everybody, but you can do it, right? So now you take one of these, and what do you get for $1 million? Well, you could get 20 petabytes, 10 million IOs per second, because all those drives are running at the same time, and really big transfer rates. So the cost curve, as you can see, is dramatically dropping because of Hadoop. That's what's exciting about it. It's that drop of cost that now makes big data accessible to us. Okay? So the general architecture for Hadoop is, this is a picture from Yahoo. And this came in IBM. We hired one of the Yahoo's guys who worked on their Hadoop, and he's one of our product managers, development managers. And so I think this picture must come from him. But this is actually a picture of the Yahoo cluster. And you can see this is all acting as one single server, right? One single system. And you can submit jobs to it, and it will just come back with an answer, right? So how is this architected? Well, at the very top, there's a high-level switch. From there, you have switches to racks. And each of the racks have 1 or 2 switches probably. Okay? And then within the rack, then you have nodes, right? We call them nodes or servers. So node 1, node 2, node 3, node 4, up to node n. And they're all wired together in this way. So in order for for a system to talk to node 6, they would go to the top switch, go through the rack switch to get to the node. Okay. And this, as you can see, can scale out almost, I wouldn't say infinitely, but scale out very, very widely, right? It's a scale out architecture. What is Hadoop? That's a really interesting question. So if you go online and you go to, you can go to IBM's website, and you can download IBM's Hadoop platform. It's called the IBM Open Platform with Apache Hadoop. It is pure 100% open source pieces only. It's got like 15 or 20 Hadoop projects in there. You go, is that Hadoop? Well, it kind of is. It's kind of what people see Hadoop is, as this giant toolbox that has a file system with it, right? But really, at the very core of what Hadoop is, if we could really break it down to the minimalist pieces, Hadoop would be HDFS, or called this Hadoop Distributed File System. it would be MapReduce and Yarn. So Hadoop, the core definition is those three things. So why a distributed file system? Well, you're going to learn, I'm going to show you how it works, is that when you store a file on Hadoop, we need to find a way to, I got a choice. I've got 10,000 servers. Where should I store this file? All right, so how do I make that decision? How do I make that file resilient to failure? How do I, so on and so forth. So it's distributed because I have a choice. I have a bunch of servers acting together as a single virtual file system. Second piece is MapReduce, which is a computation framework. Remember that complexity piece? How do you program to a system that is 5 nodes or 1,000 nodes, right? Well, for those of you who are Java programmers, what did Java do for us, and why is it so popular? Why does it remain so popular today? When I was in school, it was just catching on. Okay, that kind of dates me. But what it was is that we could write code once and run it anywhere, and that was kind of a big deal. Right? I can write into a platform-agnostic language, and I can compile it and run it on AIX, HPUX, Solaris, Linux, Windows. Right? No one had ever, really achieved that before. And so, what MapReduce does for clusters, it's a programming paradigm that allows us to write code in a way without having to think about the complexity of a large cluster. That code will run whether it's a single node or 5 nodes or 1,000 nodes. Okay, so that's an abstraction layer to coding to a cluster. And then Yarn is resource management, which I'll get into a little bit. And then there's all these kind of projects. You heard me say, well, what is Hadoop? Is it 15 projects or is it 3 or 3 components? And that's kind of getting a little bit blurry, but most people see Hadoop as having a bunch of components, and people say there's a lot of hives and pigs in Hadoop, for example. We'll get into what these are. So let's talk about how this all comes together. So it is what we call a master-slave architecture. So there's this thing called a name node, and its job is to maintain metadata. And metadata is data about data, right? So if I were to write a file, okay, and this is a large file, what Hadoop will do is take that file and break it up into 4 chunks. So I need all 4 pieces, A, B, C, and D. So to have the complete file, I need A, B, C, and D. But for resiliency, it's going to take each of these chunks, and I have a collection of data nodes, these compute nodes that have disks attached to them, and it's going to write that first chunk to the first node, second chunk to the second node, third chunk to the third node. And you'll see the part C, for example, it does not exist on the first node. It does exist on the second node, third, and fourth node. So it's kind of round robining and roughly evenly distributing across the compute nodes. Okay, so what it's doing is what we call this replication factor. The default replication factor is 3, and the general thinking is that 2 copies is not enough, because if I lose a copy, I have 1 leg to stand on, and I might not have enough time to recover. So for decent resiliency, we kind of need 3 copies. And so that's what it's doing here, right? Now that's configurable. Maybe you have data that's not so important. One copy is enough. If I lose it, no big deal. But really important data, I might make 3 copies. But something else is really interesting here is that when I run a job and I want to read that file, I can now read it in parallel, can't I? I can submit a job, and I want to read A, B, C, and D. Well, I can read A on this node, I can read B on this node, I can read C on this node, and read D on this node. That file, I can now read 4 times as fast, because I'm doing it in parallel. Follow? So I'm solving 2 problems. In addition to surviving a failure, I can have a whole node failure, or I actually have the ability to parallelize my work now. Now I mentioned, if I have a RAID array and a disk drive fails, I get an alert. I got to go and change that drive before another drive fails, right? Well, with Hadoop, it's kind of fault tolerant. If it fails, Hadoop will figure out that what data was on that disk that failed and rebuild it somewhere else. I may never repair that drive, right? And it'll just kind of rebuild somewhere else. And so that's kind of a nice thing. It's kind of self-healing, right? So there's this notion of blocks, okay? HDFS blocks. HDFS again stands for the Hadoop Distributed File System. The default is 64, but most people use 128 megabytes. And we can take a file and break it into chunks. So we'll use 64 as an example because that's the default. And we'll take a file that's maybe 210 megabytes. Remember that A, B, C, and D? Well, there's my A, B, C, and D. And we'll take those chunks and distribute it. Now, if I have this tail end, that last part that's 18 megabytes, is not quite a 64 megabyte block. That's okay. It's only going to use what's required to store that file, okay? Now, there's a saying that Hadoop doesn't like small files. Anyone know where that comes from? Any ideas? Say again? What's the point of using? Yeah. So I guess my point is this all sounds really cool, but now I threw this at you, right? Okay, Hadoop doesn't like small files. Well, the reason is because I have to maintain metadata for each of these chunks. I have to remember chunk A is on this server, chunk B is on this server, chunk D on this. So what was formerly one file, I now need to remember 4 pieces. But each of those blocks are replicated 3 times. So now I got 12 things to remember, right? Now, so this is one of the kind of drawbacks of HDFS is that actually it's not really efficient handling lots of gazillion of small files. This thing, this name node, which has all the metadata, can get choked up with, if I have to maintain a small entry for all the small files, it gets choked up with, you gotta keep all that in memory. The name node works best when all the data is in memory. So what we can do, of course, is, just some grooming, right? We can combine the small files and to free up space in the name node. But we're dealing with big data, so the general thinking is that we're going to try to land big data sets into this platform.
I have a question.
Sure.
What's considered a small file? What's the size?
Well, if the block size is 64 megabytes or 128, that's configurable, right? So anything less, so a small file would be anything that doesn't utilize that.
So it's going to be 64.
Well, no, I take that back. It's really just, I can't remember how many bytes it is, but per entry, it'll take I think it's like 100 some odd bytes per tracking each one of these things. And so it's just a matter of having too many of them. Then you can either increase the memory in your name node or beef up your name node, or you can combine your files to kind of to free up name node space capacity, right? Okay.
So tweet sizes are too small?
Well, the tweets typically come in as this big stream of JSON, so they can be combined if they're not already combined. Yeah, you stream. There's ways to bring in small data sets and land as large file. There's a tool called Flume actually that can allow you to combine them into a buffer before you land it. Yeah, question? This one? Okay. Yeah. I wouldn't see this as, so the question is, just because I'm done with this doesn't mean I'm done with the whole file. And I wouldn't see this as rows. I would just say that from a placement perspective, that block A exists in 3 places for resiliency, but also it gives me the opportunity to read the entire file 4 times as fast, because when I get to MapReduce, this will be more evident maybe, because this file, let's say this file, let's say it's just a rows of records, okay? Stuff like maybe it's a system log or rows of records that came from a database, right? Maybe a CSV file of some sort, right? And I want to just calculate something like a summation. I want to sum the value of a certain column, right? Well, I can read this in any order, right, to get the same answer. But because I've got A here, and I've got B here, and I've got C here, and I've got D here, right? Each of these, we're going to show you how we can actually calculate the sum at this level, and then aggregate up so that it's parallelized. So we kind of get sub-answers at a lower level, and then we combine the sub-answers to give us the final answer. So having the block exist in multiple places allows us to parallelize the read. That's the basic point. Show you an example, okay? So there's also the notion of rack awareness too, okay? So remember that picture that had lots of racks in it? Well, we could survive a rack failure too, because maybe it's got a bad switch. It's unlikely that my whole rack will go down, but maybe I have a rack with a switch and there's some problem there, right? So what I can do is I can take that block A. These are rack 1, rack 2, rack 3. I have block A on the first node. The name of them will say, okay, I need to write this to a different rack because I have more than one rack available to me, so I want to survive a rack failure. You can write to node 5 and node 6 where there are on a separate rack. And so now I can survive the entire rack when failing, and I still have copies on rack 2. Same thing for B and C, right? So the name node is tracking which blocks are on which rack, okay? And so this will help your workloads to choose where to run the workload. So now I get to the MapReduce part. So this is the abstraction layer, right? That allows us to code to this compute platform without having to worry about whether it's 1 node or 5 nodes or 1,000 nodes. And so basically, there's this thing called map. And map you can think of as applying to breaking up the work across the nodes. Now, if you're a Java programmer, there's this MapReduce interface where basically there's a map API and then there's a reduce API, and it gives you a line of data, and then you decide what do I want to do in the map phase. You implement that. What do I want to do in the reduce phase? You implement that, and then you deploy the code and you run it. So the whole point is that when I write that code, I didn't have to think about whether it was a multi-node cluster or a single node cluster or the size of it. It's taken care of for me, right? Now, so the map phase will take that code and run the code on a subset or even all the nodes, and it's breaking that job into small parts. Remember, my files exist as chunks across the cluster. Then there'll be this shuffle phase where we're kind of getting the data organized. We've pre-processed the data. We're going to regroup the data in this shuffle phase where data gets moved around. And then we can do this thing called reduce, where the sub-answers then are combined, and I get my result set back as a single answer. So that in a nutshell is not MapReduce. Now I should mention that MapReduce is more conceptual. Like Hadoop didn't invent MapReduce. MapReduce existed before Hadoop. It's really just an approach to solving a problem. But I think Hadoop and MapReduce together kind of is what kind of gave its fame and interest. So we're going to talk about Spark, for example, and Spark has map and reduce functions too, but it's not Hadoop, right? So what happens? So what we have is a client application, and maybe the client has a simple question like, hey, how many times does the word hello appear in a file? Remember, everything in Hadoop is a file. So what will happen is it'll spin up what's called an application master, which is kind of like a quarterback to the whole process. It will talk to the name node to figure out, this file, wordcount.txt, where does it live across my cluster? And then it will spin off these map tasks to run on those compute nodes. And each of these nodes, which have a piece of that data, will then come back with a count, right, of their own. And then what will happen from there is, in the reduce phase, those sub-results get aggregated back in the reduce task, and the result is sent back to the client through a file. Okay, so that's essentially MapReduce. Every big data analytic, almost every big data analytic, I would say, it kind of comes down to this, right? When we have big data, we're not looking at all the data. If you hand someone a report with 1 billion rows on it, here's the data you asked for, they're not going to do anything with it. Often in big data, it's taking a load of data and trying to aggregate it, or summarize it, or group it, or average it, or something like that, right? So MapReduce is conducive to that. Okay, so with that, I put in this slide for break time. I'm trying to get my internet connection working, so hopefully I can show you how to get your own environment for free, but I need about 10 minutes to try and figure this out. We'll take a break. Let's come back at 7:25, okay? All right, thanks.